Good afternoon and welcome to today's webcast. Our topic today is Analyze and Optimize 32 to 56 gigabits per second serial link channels, sponsored by Keysight Technologies, Xilinx, and Wild River Technology. I'm Chris DiMartino with Penton's Design Engineering and Sourcing Group. To begin, let me explain how you can participate in today's presentation. First, if you have any technical difficulties during today's session, simply hit F5 to refresh your webcast console. If you need assistance solving common issues, please click on the yellow help icon located below the slides. To maximize the slide presentation window, click on the small green button at the top right corner of the slide window. Please know that we welcome your questions during today's event. We will answer as many questions as possible during the Q&A session that will follow the main presentation, but feel free to send in your questions at any time. To do so, simply type your question into the question window on the side of your screen, then hit the submit button. Additionally, today's session is being recorded and will be emailed to you within the next week. You may also download a PDF copy of the slides by clicking the green folder icon in the toolbar beneath the slides. Now let me introduce today's speakers. Heidi Barnes is a Senior Application Engineer for High-Speed Digital Applications in the EESoft EDA Group at Keysight Technologies. Alfred Neves is a Chief Technologist at Wild River Technology, and Jack Carroll is an Applications Engineer at Xilinx. Now let's begin today's discussion. Jack, the floor is yours.
Thank you. I want to begin our presentation by framing it as an application. Let's say that we want to have some product where we want to communicate between two cards that are plugged into a backplane. And to move a lot of data, we want to use a serial I/O over those channels. And immediately we begin to see that there's a structure to that. We're going to have the daughter cards and the traces on those cards and the attenuation that they represent. We're going to have connectors and the reflections and crosstalk that are involved with using those that have to be understood. So let's say in this application we choose to use the 100G base KR backplane interface as the basis of our design, where we run multiple lanes at 25 gigabit and to transfer the information at an effective throughput of 100 gigabit. In the 802.3 spec, there is some information on how the specification views the channel and provides some points in the channel for discussion or emphasis. And that the channel itself is described as coming from some device mounted in a package, the package mounted on a board, and then the board connected to some backplane interface, and then the reverse happens on the other side into the receiver. So each of the four lanes are going to represent this basic structure. 100G base KR also addresses testing, which gives us an idea of those things that we need to understand when designing and implementing this kind of interface. We have to understand that there's going to be some channel ISI or frequency-dependent channel loss that's going to affect the symbols that we're transferring. There's going to be some channel noise sources that we need to understand that get applied to that signal channel also. And we want to characterize the transmitter itself and also to characterize the channel from one end to the other. The spec also covers some basic design criteria, including the insertion loss limits for such a channel and the differential return loss. So we're giving a lot of specifications that should hopefully lead to a successful implementation. There's a lot of details to that. You've got the transmitter. Its signal has to propagate through some package substrate. There's a BGA escape on the printed circuit board, most likely through a via to a strip line layer, and then routed over to some connector, propagating through a via at the pins of the connector, and then getting into the backplane through a via, and then reversing that whole path to get to the receiver. So you've got all those pieces that have to be considered and implemented for your channel. And then having done that, there's no guarantee. There's still a lot of pieces that you have to understand. And so if you end up with a link that doesn't come up, then we want to address a methodical way of troubleshooting it. First of all, understanding the pieces of the system that make up that serial transfer or the SerDes link is you've got power supplies that are specifically supplying voltage for the analog circuits in the transceiver. You've got a reference clocks either at one or both ends of the link that provide the timing for the transmitter and the receiver. And all of these need to be verified for connectivity and for their compliance. Think of the SerDes link as a 4-port device or block. You have the power supply, specifically the analog power supply for the receiver and transmitter. You've got the transmitter and receiver input and output port, and you have the reference clock. So we want to look at each one of these. For the power supplies, you'd want to, the noise on the analog power supplies on these transceivers tends to be stringent. And so you want to measure it, but it's not an open band measurement because really the circuit is most sensitive in the tracking range of the PLL in the transceiver and in the tracking range of the clock recovery circuit in the receiver. So by limiting our measurement, we can really look at the power supply the way the circuit looks at the power supply. And usually that's below 100 megahertz in the 10 kilohertz to 100 megahertz range. So you band limit the measurement. That's going to keep you from troubleshooting and putting effort into addressing noise that maybe would not be affecting your circuit. It also makes it easier to detect what's going on in your power supply. And you can band limit it by either using an external low-pass filter or some power supply, some oscilloscopes have a real-time function for processing and applying a low-pass filter to your data. You also want to measure the reference clock, and you can do that by measuring the jitter or phase noise of the clock. By configuring the transmitter to send an alternating 1-0 pattern, a square wave, it allows you to eliminate any frequency-dependent intersymbol interference as part of your measurement, which would not be a clock issue anyway. And you can then focus on either measuring the RJ using jitter analysis, or you can look at phase noise, and you can look at the phase noise directly, and you can convert that to RJ also. So you want to especially look at the PLL tracking frequency, which might be 1 to 10 megahertz in bandwidth, you want to look for significant spurs at higher frequencies, and you want to calculate the RJ just to be as a sanity check on the quality of your phase noise measurement. So when we make these phase noise measurements, we get some carrier frequency, which is going to be, let's say it's 25, or in this case for this phase noise, it's a 10 gigabit per second signal, and so it's the carrier is actually 5 gigahertz, and you can scale that carrier back down to the reference clock rate, because the PLL is going to be multiplying the reference clock up to the output line rate. And you use the relationship I show here, where you take 20 times the log of the output carrier versus the input carrier frequency, and you add that to what you're measuring from the carrier, the transmitter output. And that would reduce down to the phase noise you would measure if you were measuring it at the frequency of the reference clock. And I've shown that conversion here to where the blue line represents the phase noise at the rate of the reference clock, which in this case was 500 megahertz. So there's a mask usually involved with selecting the reference clock. And we notice in this case when we make the measurement that the converted phase noise actually exceeds the mask that was specified for the reference clock. If we measure the reference clock directly, which is the additional trace that's light blue here, we see that at low frequencies, the PLL is actually tracking the reference clock. So that seems to be the cause of being above the phase noise mask. If we take a very good oscillator, like here, and I have a very low noise reference clock oscillator, and I use that with the transceiver, I get the red line up here with a lower phase noise at those lower frequencies. If I take that output of the transmitter and then scale it like I did the other one, I get a phase noise that's below the mask for the reference clock. And so you see we've shown that our reference clock here could have been a cause for more jitter than maybe we expected in our circuit. So we've talked about the power supplies, we've talked about the reference clock, and now let's talk about the channel. And I'll let Al Neves take it from here.
Hello, my name is Al Neves. Can everybody hear me? Okay. I'm the Chief Technologist at Wild River Technology. And as Jack implied, the backplane is extremely complicated. When you want to optimize the backplane or optimize the SerDes and analyze the backplane and develop a cohesive optimization and characterization strategy, complicated and non-systematic is not very well, doesn't lend itself to good engineering practice. However, at the end of the day, the SerDes needs to work with the backplane, so I'm not precluding that or suggesting that. It's difficult to form a coherent optimization strategy and establish clear margins versus issues in the system. A simple example would be crosstalk. If you have crosstalk aggression through, let's say, one of the via fields for the connector, and the SerDes has an error problem, is it because of the mode issues that are created, or the coupling, or the impedance bump, or is it the crosstalk energy, or is it a combination? That makes the problem very complicated, and a simpler way of looking at the system is what we're going to be talking about. Jack came up with this comment that really hit hard. It's all about the margins. In doing this work, and he lives it every day, you're always trying to determine what the margin of the system is and what impacts that margin. This is an example of the UltraScale TX and RX running at 32 gig. We replaced the backplanes with some test platforms. The test platforms embody a concept of pathological design space. I'm going to discuss what that is in a minute. The structures are as simple as possible, and they're extremely high signal integrity, except for one pathology and the circuit. All the launches are pristinely designed. And what the objective is to isolate pathologies and build problems one at a time in a systematic way, and then re-optimize and analyze your margins so that you get a consistent and systematic characterization and strategy for optimizing the channel. And then at some point, depending on how much return loss, degradation, loss, crosstalk, or combinations thereof, the system runs out of margin. But you can completely understand where that margin goes to zero. We'll be talking about that a little bit later. So what is the pathological concept? Well, it's an analogous concept. Imagine a very healthy person. I don't mean to be dark, but imagine a healthy person walking into a doctor's office, and the doctor says to him, well, you have a problem. And the guy says, well, I'm very healthy. And so from a circuit standpoint, you have a very healthy or very high signal integrity circuit, but you include one pathological element. However, the overall signal integrity is really very good. They represent a family of structures, and you start off with a root structure like a through. And this whole approach lends itself for doing de-embedding, and it's also very EDA friendly. And the through establishes a reference and helps you model the entire system. The importance is to be able to model the system and to be able to run it and have measurements and simulation run cohesively. In addition, comparing that to the internal tools of the SerDes. And I'll be talking about that later also. So here's an example. So the simple diff through on the left is just a simple differential through. The circuit on the right is the same exact twin except for one thing. You've added a ground void. Now, what does that asymmetric ground void do? Well, it adds STD1 degradation and mode issues from differential to common mode degradation. So what I could do is I could run a system with the left, simulate it, optimize it, and then I can add the circuit to the right and replace it with the circuit to the right, and now I see the addition of one pathological element, which is the asymmetric through. So there are benefits to this approach. You improve your SerDes characterization. Even in this study that we've done with Keysight and Xilinx, I believe we've learned some very interesting things using this approach. You're actually also able to improve the manufacturing because you can use elements of these pathological structures in your test, your product engineering, your characterization engineering. And you also can drive design tweaks. For example, if you very, very accurately state how much loss the SerDes can sustain before running out of margin with very good return loss, you can report that information back to the design organization, and that information is unimpeachable. It's basically loss without return loss, or very good return loss characteristics. you can improve your measurement simulation correspondence, and it also provides an IBSA model, pathological space correspondence. Now, I'm not really marketing this. I mean, this is, obviously what my company markets. You can create these circuits for yourself as long as they follow and it's not really actually that complicated if you know how to do the signal integrity design. I keep hitting the wrong button. Okay, that's the right button. Here's an example of a two-dimensional pathological space. Look at the system on the right. That's an inter-symbol interference platform. I'm going to create a two-dimensional space of pathological space with loss that I can change or crosstalk on the y-axis. And I can add combinations, and we'll show examples of that. And this is an example of a two-dimensional pathological space. I can actually eliminate the structure, the structures on the left, which is the crosstalk structure or crosstalk platform, and have a one-dimensional space of just insertion loss. Or I can add the crosstalk, and I can also add another element from the crosstalk where I can actually add degradation of return loss. And there's going to be some discussion on adding return loss degradation on top of crosstalk and insertion loss, which would make that a three-dimensional pathological space. Here's an example of systematically adding structures. You'd start with a clean, very pristine low-loss channel. You would add moderate loss. And maybe you could add random jitter or return loss degradation or crosstalk, or you could back out or add combinations in this. So you can systematically add and subtract pathologies at will and then recharacterize and reoptimize the channel and resimulate. Here's an example of a crosstalk structure that's a bit novel. Typically when you have crosstalk in a system, you have other issues. You have mode issues, you have impedance bumps, things couple. So the receiver noise, the receiver sees noise or crosstalk energy, but it also sees some other things. And those other things may cloud the characterization of pure crosstalk. So the question is how much does the SerDes, how can you characterize the SerDes performance and optimize the channel with pure crosstalk energy? And this circuit does that. It's optimized for 100 ohm differential, and you can add far end, near end crosstalk. And there's a host of these from 0.5 width out to 5 widths for very low crosstalk or very, very high crosstalk. And they're all optimized for the same return loss. And here's the plot. So you can see that as I change the structures in the left from 2 widths to 4 widths, I change the far end crosstalk, but I still map the same return loss. So if I change the structure, the only thing I'm changing is the crosstalk. I'm not changing the return loss characteristics, so I'm not clouding my characterization issue with return loss variations. So in summary, pathological approach uses high signal integrity structures with isolated issues. You add those structures in a systematic way to improve the methodology of determining your margins in the system and creating optimization strategies for SerDes. We're going to be at DesignCon next week. We invite you to be at DesignCon, and then we're going to do a 3.5-hour version of this, and I look forward to meeting everybody. Thank you.
Heidi, we will need you to unmute and begin again, please. Oh, sorry about that. Thank you very much, Al, for bringing up this new term of pathologies. We're going to take a closer look at how these pathologies affect our design margins in both simulation and measurement. And we're going to do that by gaining insight with the pulse response. So first, let's start with a little bit of basics. We have the well-known impulse response here, and most people are familiar with the delta Dirac impulse response, and we can put that into a channel, into a system, and we will get an output, y of t here. And basically that output is just this impulse response convolved with the behavioral transfer function h of t of that system. This is based on linear time invariant systems, and it's a very well-known mathematical approach to describing a system and what the output will look like based on an input. We can, instead of the impulse function, we can actually send a single pulse or a single bit through our channel. And the reason we want to do this is the single bit actually represents the data that we're trying to send through. It's based upon our unit interval and a single 0 to 1 or 1 to 0 transition. This provides us with very quick insights into how hard is the receiver working to recover the data that we're sending through that channel. There's also some really interesting things that you can do with this pulse response. One of the benefits that it has is that we can use this to look at how an equalizer works. The pulse response here is showing us how the feed-forward equalizer is working. And you can see here in the upper left, we have sort of a description of how the feed-forward equalizer works. There's a precursor that can help improve or sharpen up the rising edge, improve the rising edge of our single bit. And then there's a post-cursor section that we can improve the falling edge. And then, of course, there's a main cursor tap to control the amplitude. When our ideal pulse goes through a channel where there's lots of degradation, you're basically getting a lot of frequency-dependent losses, and therefore it's degrading both the rising and falling edges, and your single pulse or single bit no longer fits in one unit interval. It's actually spreading into the preceding bits of information and into the post bits of information. And so in this way, it's very difficult for the receiver to recover the exact ones and zeros because you're degrading the bits on either side of this single pulse. So what does the FFE do? This feed-forward equalizer is a specific type of finite impulse response filter, and its ability is to sharpen up the degraded pulse and bring it back to look more like a single unit interval. And what's interesting is with the single pulse response, you can very clearly see how this equalizer is sharpening up both the rising and the falling edge, and what happens if you use too much equalization. You'll actually see some overcorrection or dip right before the rising edge, and then too much amplitude correction afterwards. What's also interesting is we can look at the spectral content before and after applying the equalizer. And on the right here, you can see that the feed-forward equalizer is actually reducing the amplitude or attenuating the low frequencies in order to peak or increase the frequencies, the higher frequencies. So this is a thing to be a little bit careful about. You're losing some amplitude, and then you're actually also increasing some of the very high frequencies. So something to think about when using the feed-forward equalizer. There's a little schematic here that shows how this is a back channel type of operation. You're actually doing some signal processing where you're delaying your bit stream and adding in that correction before and after the bit as it goes through the system. That was the feed-forward equalizer. Now let's take a quick look at the pulse response of the decision feedback equalizer. Again, a lot of insight can be gathered by using this single pulse response going through the channel. We have here on the left, the gray is sort of showing the single unit interval, what our ideal pulse width would be. The red is the degraded pulse that's come through our channel, and you can see that we have this red single pulse is smearing into the preceding and trailing bits. And with the decision feedback equalizer, we see very quickly that it's does not do anything to the rising edge. It's a slicer type of correction where at each transition it knows what bit it had just received, and it's slicing to correct for that falling edge, or I should say the slow tail sort of transition there of that bit. So the decision feedback equalizer really only helps us on that falling edge here. And what's interesting, again, if we look in the upper right and we look at the spectral content, the decision feedback equalizer does not actually attenuate. This is all done in signal processing, and it's not attenuating our signal. It's really just adding in a faster falling edge there and adding spectral content in at the higher frequencies. So it's a very efficient method of equalization and correction that can happen at the receiver. The decision feedback equalizer is at the receiver, and the feed-forward equalizer can actually be done at the transmitter. So keeping that in mind, let's go ahead and take a look at measuring our channel or simulating our channel. If we're going to do simulation, we're going to be hooking up a transmitter, and we want to insert these different pathologies that Al Neves was just talking about in terms of ISI material transmission line type loss, as well as crosstalk and return loss type pathologies. And then we have a receiver that we'll connect up to. But first, let's take a quick look at what bandwidth do we need for these cascaded S-parameter blocks. And this brings up a very good question. There are a lot of rules of thumb there's rules of thumb out there. Then the question is, do they really help? So if we have a data rate, say 32 gigabits per second, and if we start over here on the left and we want to know what is really the bandwidth of this 32 gigabit stream of data, and if it was just a sine wave, if we only had one frequency, that sine wave would actually be down around 17 gigahertz for a 32 gigabit signal. But if we want this data pattern to sort of have a square wave shape, or to get at least square up those edges, we would need a third harmonic at around 48 gigahertz. And then if you read a lot of your signal processing theory, you would say, oh, I really would like a fifth harmonic, because that would make it look like a real square wave, or a lot closer to it. But that's up at, say, 80 gigahertz. And it's nice to say, it would be nice to have the fifth harmonic, but there's a significant cost in taking those measurements, and even in simulation speed sometimes, to go up to these higher frequencies. So let's take a closer look at some of the other rules of thumb. Obviously, if it was just a sine wave, if we look at that 20 to 80% rising edge for a sine wave, we would find that frequency is only 0.2 divided by the rise time. And if we look at a rise time of a RC tank circuit, this is another way of estimating it, because most of our circuits and our transmitters are charging up some sort of capacitor. And so this has been a long time rule of thumb that you look at that RC charging time, RC tank circuit, and basically it's the 3 dB frequency point, and that 2080 rise time works out to be 0.22 divided by the rise time equals this Nyquist frequency or bandwidth. It turns out that this bandwidth step response RC tank circuit, this gives you roughly a frequency of around 17 gigahertz, which is not enough, as you'll see in the next slide, is not enough bandwidth, while the third harmonic may actually be too much bandwidth. So one of the things I found very quickly is that the amount of bandwidth you need depends on your rise time of your transmitter. It also depends on what data you're actually sending through the channel, what's the spectral content of that bit stream, and more importantly, it also depends heavily on how your simulation tool is handling those S parameters. Does it use a Fourier transform with non-causal windowing type effects, or is it using a more sophisticated Hilbert transform with causal and passivity enforcement? And one of the things, the demonstration I have here in our ADS simulator, we use the very robust Hilbert transform with causality enforcement. This lets us use S parameters with a lot lower bandwidth than, say, a simulator using Fourier transform technology. But even so, even with this very sophisticated handling of the S parameters and the transformation to the time domain for seeing how a bit pattern goes through our channel, you can see if we band limit all the way down to 16 gigahertz, this is the Nyquist frequency at 32 gigabits or 56 gigabaud data rate for PAM4. I'm showing the PAM4 example here, and you can see with 16 gigahertz Nyquist frequency, obviously the eye looks deformed, but it's the single pulse response that allows us to actually see how the simulator is struggling with that limited bandwidth and a lack of time step resolution to recreate the pulse. By going up to 32 gigahertz, this is still less than 3 times our Nyquist frequency, but it is more than the rise time, 2080 rise time estimate with this 13 picosecond rise time. So by using our simulator, we can find that we only really need to go up to maybe 32 gigahertz, and we get a very good representation of this PAM4I. The third harmonic estimation on the right here goes up to 48 gigahertz. This is our third harmonic at 56 gigabaud. And you can see, obviously, our pulses are now very clean and recreating here. So that was a brief message on what bandwidth I need. The short message is that you do actually need to put it in your simulator and try the different bandwidths to see how it is handling the band limiting for that application that you're interested in. Now, the next step in simulating our channel with the different pathologies is to make sure that we have a good transmitter and receiver models and that we have actually set them up correctly in our simulator. Now, good IBIS AMI models like the ones that we've obtained from our partners at Xilinx for the UltraScale Plus device, they have a very nice IBIS AMI kit example that you can set up in your simulator, and you can see that on the left. They provide that data, and then on the right is the setup in the ADS simulator, and you can see how we've recreated the exact channel that's in their example and the data that they also get. Now that we've verified what bandwidth we want to measure our S parameters to, and we've verified our setup is working correctly with the IBIS AMI models, now we can start putting in our channel pathologies. And here's sort of a quick design of experiments. And the title of the slide is All Loss is Not Created Equal. And the important point here is that I'm looking at 3 different lossy channels. The first one has minus 35 dB. You can see that in the green on the right graph here. The next one is minus 40 dB. That's the blue and the red. And then minus 50 dB. 3 different losses. What is very interesting is I can add crosstalk to the minus 35 dB channel, and it does not change the loss at Nyquist. On the minus 40 dB channel, I could add additional return loss. You can see a lot of amplitude variation in the red trace here at low frequencies, but it still only has the same minus 40 dB of loss. So even though these cases might have the same loss at Nyquist, they may have different pathologies going on. We can take a look at actually applying one of these pathologies, and this is a very interesting case. We're going to show by looking by adding in a crosstalk pathology that we really want to minimize the transmitter equalization and really make the RX equalization do most of the work. And let's see how this works. We have a crosstalk. We've added a channel that has crosstalk, and you can see here has minus 35 dB of loss at Nyquist, and there's some crosstalk signal. Up on the top here, the first eye diagram is with the transmitter precursor set to 3 dB, and it's in the presence of this crosstalk. Now what's really fun to look at is this graph on the right of the single pulse response that the RX receiver is looking at. That's this blue pulse. Each one of these grid lines is actually indicating a unit interval. So you can see how this blue single pulse response is spread out across close, to 6 or 7 bits here. It's been a significant channel degradation on this single bit, single pulse. And then the red trace is actually the auto adaptation equalizer, DFE and CTLE on the receiver is able to take that blue pulse and turn it into a single pulse response that actually fits within the unit interval now, and we can recover the fact the 0 to 1, 1 to 0 transition. So you can really see how much benefit here that DFE is actually doing. Now the interesting part is I might think, great, equalization, it's doing all sorts of wonderful things here. What happens if I turn up or increase the equalization on the transmitter and I go to a 6 dB precursor? I would think that maybe that would help improve my rising edge here on this pulse. It turns out it does very little. It may even hurt the eye opening by increasing the equalization on the transmitter. And the reason for this is in the presence of crosstalk, that loss of amplitude caused by the feed-forward equalizer, it's decreasing the amplitude of my pulse, but my crosstalk amplitude is not changing at all. And so in relation, in fact, the rising edge may also increase some of that crosstalk if I'm speeding it up too much. So in this case, you have to be very careful about turning up your equalization on your transmitter in the presence of crosstalk. So now let's go ahead and see what happens when we do some measurements. And here's some additional insights that you can gain. If we do some an actual hookup to the hardware, hookup to the test platform crosstalk channel from Wild River's technology, and we run our Xilinx UltraScale Plus transmitter signal through that channel with minus 35 dB of loss, no crosstalk to start with, we get a certain eye opening. And then we can add an aggressor that's adjacent to that channel at 200 millivolt aggressor. We can add and we can increase the aggressor to 670 millivolts, and then we can increase it to 940 millivolts. Now what's really exciting to look at here, this is a 32 gigabit per second signal, PRBS 15, and in simulation we showed how we really don't want to maximize our TX precursor, so we're using the 3 dB of equalization on the TX, and we have our auto RX decision feedback equalizer. Now we have a plot of how the eye on the left, we're looking at how the normalized eye degrades as we increase from minus 35 dB of loss to all the way up to 50. So in this plot here, we started with a normalization of the eye at minus 35 dB, no aggressor or crosstalk, and we kept adding more channel loss, and we can see how the eye opening degrades all the way up to 50 dB of loss at Nyquist. Now what we're going to do is look at what happens when we add in our 200 millivolt aggressor, and we can see that the eye opening of when we add in that aggressor is equivalent to a channel that has roughly 40 what do I say, 44 dB of loss at Nyquist. It's roughly a 10 dB penalty there. If we add in an aggressor at 670 millivolts, this is about roughly a 12 dB penalty. And then finally with our 940 millivolts. So if we have an aggressor that has a fairly high amplitude sitting next to our channel, we can get as much as a 15 dB penalty of loss. This is giving up a lot of margin in terms of actual length of a backplane. With 15 dB, I could add at least a couple more inches onto my backplane. But if in the presence of crosstalk, I would be giving up that extra length of routing. I'd have to shorten up my traces and reduce the amount of ISI loss to accommodate for the additional loss of crosstalk. So very interesting things that you can do here in terms of looking at the different pathologies by themselves and systematically adding them in and seeing their effects. So the result here is that crosstalk also steals the margin for the insertion loss. So in summary here, Jack did an excellent job of talking about the signal integrity of a channel and how it must include the analysis of all types of margin-eating pathologies, not just channel losses, but also clock noise and power supply noise. And then Al introduced the pathological term to give us some insights into how to break apart the signal integrity, and this approach breaks down the signal integrity of a SerDes channel to isolate sources of degradation for better optimization of design margins. And then finally, I've introduced the pulse response as a new way to evaluate band limit S parameters and equalization techniques, as well as to provide valuable insight for optimizing SerDes channels in the presence of crosstalk. So with that summary, and Al sort of already gave you some preview of this, we'd like to thank you all for attending, and we would all look forward to seeing you at DesignCon next week. We actually have a 3-hour tutorial on Tuesday, January 31st from 1:30 to 4:30 p.m. The title is 32 to 56 gigabits per second serial link analysis and optimization methods for pathological channels. So if you like this webcast today and you want to hear more and meet the speakers, please come to DesignCon next Tuesday and meet us. Also, if you can't make the tutorial, stop by our booths and request a booth demo. Wild River Technologies will be at booth 850, and Keysight Technologies will be at booth 725 at the entrance. So with that, there are some links here for you to gather more information, and I believe we're now ready for to answer some Q&A.
Thank you. Now, before we begin the question and answer session, we would first like you to help us improve our webcasts and answer a couple of short questions about what you saw today. In the slide window, please select the answers that you feel are best. Question number 1, please rate your overall satisfaction with this webcast. Question 2. Based on what you heard today, would Keysight's advanced design system have value in your work? Question 3. If you do have an interest, what would be your time frame? Thank you for your responses. Now on to our question and answer session. Question number 1. Where are you seeing more challenges with the higher 32 gigabits per second designs? Is it in the PDN design in clock jitter or XTalk due to routing challenges?
I think that mostly we're seeing routing challenges driving people to bring up a circuit, and probably second to that would be jitter from the clock circuit itself.
Okay, next question for Al. In the examples of connecting different test structure channel pathologies together, how important is the phase matching quality of the cable pair that is used?
Well, the obvious answer is it's extremely important. I mean, the unit intervals are down, 30 picosecond. We've been doing a lot of work with cables and cables that work consistently for different setups. And, it's a bit of a loaded question because, my company markets low skew cables, so talk to us separately. But what we basically found is cables are very difficult to build and design for jitter. They have to have low skew because the SerDes is extremely sensitive to skew in terms of characterization. Secondly, as you twist the cable, the phase has to stay stable, or as stable as possible. So we use an IEC mil specification. Third, it doesn't change 20 degrees or more on our cables out to 50 gigahertz. And then we also found that we have to TDR in addition to checking return loss for both sides to make sure that they're matched and that the construction of the cable is done correctly. I see a lot of people building $100 million SerDes and using $2 million worth of capital equipment and then just blindly grabbing cables like from some place in the lab and not checking their cables, and that's not really helping them.
Okay, the next question is for Heidi. If we are unable to attend DesignCon, is it still possible to get the full tutorial slides?
So obviously we can't provide any of that until after DesignCon is over, but we will be following up with the attendees for this webcast with some links and an email after DesignCon is completed, and we will have links to where you can download the slides for the tutorial. There were also some questions. We do not have any plans to record the tutorial at DesignCon, so it will just be the slides available afterwards. And then one other comment is this webcast obviously is being recorded and available at a later date, and those links are provided on the last slide of our presentation.
Okay, here's the next question. What type of vias are recommended for these high speeds?
So Al, would you like to take that one with your test platform boards?
Yes, I can do that. There are several considerations for a differential via. One is localization. Okay. The second is the via has to have low return loss. The via design is a close cousin of launch design and it's a great question because it represents one of the major cruxes of high-speed signal integrity. You get crosstalk issues through your connectors to the via fields. So when we design our vias for our channel modeling platforms and we're designing a tuned via, we use a tool that optimizes the return loss. So we obviously at these speeds have to do either blind vias or what we do mostly is back drilled. And you need to use a good vendor because the crappy vendors, which we've run into a lot, have had problems with doing the back drilling accurately. So I think I answered your question. They need to be localized. They need to be low return loss. And, you know, the pad, the anti-pad, the spacing, the drill diameter, and all of that needs to be done correctly. And they need to be back drilled, otherwise you'll have a quarter half-wave resonance that wreaks havoc with these systems, especially a 56 gig PAM4, which is very sensitive to via signal integrity issues.
Okay, here's our next question. How does the RCVR determine the proper combination of equalization and settings of CTOE, FFE, DFE to optimize channels?
I'll take that.
Yeah, thank you, Jack.
The Xilinx receivers have an auto-adaptation algorithm in them. It is proprietary, but from our testing, we can set that algorithm up to choose the best tap settings for the equalizer. And also we have a wizard tool for when you're programming the FPGA, that if you can feed it some of the characteristics of your channel, it can preload some of those settings and to achieve optimization.
Okay, the next question is in regard to the added crosstalk and its equivalent insertion loss penalty. In what ways can or cannot this be considered in channel design?
So I can go ahead and take that one. Basically, we were looking at this new technique of being able to mix and match pathologies, and we were looking for a qualitative way of quantifying, what is the impact, how much margin is it actually eating. So this is sort of a new technique, and we're still exploring, but it does give you a little bit more of a way of measuring how much impact, say, crosstalk has or return loss has compared to traditional just ISI loss of a material or skin effect type losses. And in this way, we're hoping that these types of insights can provide more information in terms of what are the most important margin-eating pathologies and which ones you really need to spend money and time on fixing. So again, that's sort of the main point of this webcast, is how you gain insights into improving your channel and gaining margin and understanding where the biggest bang for your buck is in terms of making for a robust design.
Okay, well that concludes today's presentation. On behalf of Electronic Design, I'd like to thank Keysight Technologies, Xilinx, and Wild River Technology for sponsoring today's event, and of course all of you for joining.